Good. So let's start our last topic of this course, and this will be called recursive estimation. The whole idea and the whole question is: we have our plant, process, or system, or whatever, of which we have understood in some way. Let's say if we conducted an experiment, we selected some independent variables, their values, we got the true response of this system, of this plant, and we tried, based on what we have seen in the experiments, we try to find out some model that could predict these historical data. Of course, well, predicting historical data is fine, but not that much useful all the time. So we hope that if we just try to now unroll and deploy this model in some industry, this model can now tell us what's going to happen with the plant, with its outputs, if we are now trying whatever inputs, whatever values of the independent variables. Basically, we hope that even at some point in the future, where if we compare these, so if we calculate something like estimation error, then this will be approximately 0. Estimate, let's call it prediction error. What if this will not happen? And let's start with a very basic situation. I don't know exactly how to draw it, but well, let's say that our historical data might have looked like this, and our model, our fit, this is what we got. And maybe there is some part of the space of our independent variables that was not explored in our training data. But in the reality, maybe our plant would evolve like this. So we have something like a systematic error. It might be a consequence of the plant being nonlinear, that suddenly our real measurements are saying, well, we have some constant, almost constant error. Yeah, so let's say this was our training part, or we can even say it was our nominal part. Yeah, nominal, because so we are either we have some deviation from the nominal situation. Let's say we were producing in our plant, in our industry, from one supplier of the reactants, and now we change the supplier, and there is some change which causes also our plant to change. But this situation doesn't look very scary or very tough to fix. Because, well, our error looks almost constant. It's approximately constant. So what would you say? Let's say our model looks like this. What can we try to fix our model to adapt to the new situation?
We add
minus the error. Yeah. So.
Subtract the error.
Yeah. Our model was calculated. These parameters A and B were basically calculated from the historical data, and from how I suggestively draw it, it seems that the slope is actually quite okay. Yeah, it's still our dependent variable, still reacts in the same fashion to the change of the independent variable in this testing or I don't know, real-time deployment. So our slope is good. We cannot change our independent variables. We can somehow try to alter, well, this constant, this offset or this bias to accommodate for the constant shift in the error. So for this B will have a different names, but for the purpose of our discussion, the very first type of recursive estimation that we can do is just to change this bias, and this is called bias update. Very much in use in the industry. They wouldn't, if they use some model of this type, they wouldn't like to change the slopes, the dependencies, because, well, let's say they are verified. But yeah, if we should change the bias, how can we approach this? Let's say that our model predictions, independent variables, and also this parameter, well, since we are changing it becomes now a function of time. So what we can easily do is how to fix this one. We can, for example, basically say that this BK would always react to what we have seen in the past and what we have predicted in the past. Yeah, so basically we are removing the error that we have seen. Let's see how it goes in the past. K minus 1 minus ax k minus 1. Yeah, this could work. Ah, no, sorry. We took a measurement. Let me rewrite it again. How's our error defined? Yk minus yk hat. No, this wouldn't work, right? We need to derive it in a different fashion. I mean, I can write it down, but it won't make sense to you. So let's say we used this this prediction for the previous measurement. Okay, -1. And well, what we really measured was this value. So this was our true measurement. Well, and now we want to compare, make a comparison of these two, and update here. This is not a mistake. Update here the bias such that it would work. So we take these two and update. So if we just subtract everything, we get yk minus 1 minus yk minus 1. That's on the left hand side. On the right hand side, of course, these two will cancel, and we have bk minus 1 minus bk, which of course means that bk should be equal to what? So our previous bias, let's just take the minus bk on the right hand side, and we take our prediction error to the left hand side. Huh? Makes sense? So this is basically a very simple mechanism that will make us, what will it do? So our former prediction, that was this blue line, is now at some point wrong. If we just change the bias at some point, we can just achieve this shift. Of course, you can ask what happens if we then do not predict the next point in time the same value. What if the error in the prediction is just caused by some noise? So there are different nuances to it. So this is our fixed prediction with this bias formula. What people always suggest is, well, this is kind of myopic. It gets really driven fast to change this one based on just one point in time, just one measurement. So we can alter it with some filtering. Filter. And this filtering is just very easy. So the new bk will be some, let's call it delta, bk minus 1 minus delta. Oops. One minus delta and this value of the prediction error, where this delta is something between 0 and 1. Basically, you are saying by choosing the delta, what would happen if we choose delta to be close to 1? Then we are basically saying we do not trust our measurements that much. We are not going to change our bias that much based on the recent measurements. But if this trend would continue, yeah, if we really see a situation like this happening in our data, then this small contribution from each measurement, they would add up, and our line would be just gradually, slowly shifting to the possibly new operating point, possibly new situation. Of course, vice versa. If this is 0, then we are just drawn completely by the new measurement. So you can think about this delta as something as a gain. Yeah, how much do I trust the information from the measurements? Yeah, if you think about this, this is something similar to let's say some P controller. What is the one way to represent the proportional controller? We have a control error, like here we have the prediction error. We multiplied with some gain, and this is how we change our estimate of a control action. This is how we change the estimate of our model. Very simple, but used in the practice. Let's now see a different situation. So, of course, well, since we had a situation where we only need to change the bias and everything started to work, now we will check the situation. What if we need to really change some of the dependencies? Yeah, so something very similar setup. We fit our model, and now at some point our data start to behave like this. So what we can think of a mechanism, basically what we are doing. Sometimes you will find this drawn as well. We calculate. We calculate our prediction error, so this is our E, and our update mechanism is just updating the model. Yeah, this is how you can somehow sometimes find it represented. It's also used in things like adaptive control. Somebody know? So let's think about the model just in this form, because we somehow intuitively feel that we should at some point try to change the slope. And let's think about the situation. Well, we have just seen n-1 measurements, or we have just seen n measurements. This was one of the simplest situations that we studied in our in our linear regression discussion. Let me wind it back. So if we were about to, these are the wonderful sums that you all remember and loved, that we formulated in the linear regression problem. We have some data y that we collected, we have our independent data x, and to estimate the value of a, well, basically we just need to solve this equation. We already made this part with b equal to 0. Did we find some better expression? No. What will be the value of a? Equal here. Is it correct? Yes. How can we find the value of a? It's just a scalar. Sorry?
Value of a, you can just add everything to one side, then divide it with that sum.
So, yeah, so a will be equal.
It will be equal to the first part.
Well, sum of y's, right?
Yes.
Divided.
Minus ending.
No, that's 0.
So slash the sum.
Sum of y divided by sum of x's, yeah? Okay, good. Yeah, so a, and let's now call it like an, like again we will give it some time index, because we might change the parameters over the time. So if we have collected n measurements, k is equal to 1 to n, how was it? Sum of y's divided by sum of x's. Okay, and n-1, well, it will be almost the same situation. We just have this sum going from k equal to 1, but not until n-1. We have one measurement less. Let's write down this properly. Sum of k equal to 1 until n. And our task now is, if you look at these, they're not directly comparable, but if the n is like 100, yeah, so most of the terms in the numerator denominator are the same. So the question would be, Question would be the following. It might not be, if the n will grow, it might not be even practical to actually take all the time 1,000 or million of the historical values and just solve this. Of course, this is easy situation. A is scalar, but if we are in the multidimensional world, this will lead to some inversions of the large matrices. So nothing very practical. It also might be the case that, well, we would be able to discover this kind of pattern, right? Because here it was cool. Yeah, we just have the last value of our parameter. We update it somehow, filtered or not, with what is the error, and boom, we have our new value of the parameter. So can we need to check the procedure because I don't remember it. Somehow make this happen, to have like a update formula. So like an is equal to an minus 1 plus or minus something. So what we can do first, well, is to make these sums to really be equal to each other, or at least look equal to each other. So of course, if we have these n elements of the sum and summends, we can always rewrite this as the sum from k equal to 1 until n minus 1 of yk. Did we take correct formula? I have different one in my notes. My notes say we should have this formula, and why is that? Why is it better to take that one? I don't see any big difference. Let's see. Let's try in this version. Okay, so our sum from 1 to n can be the sum from 1 to n minus 1, and of course what we are missing is to add the last measurement, y at the time n. The same we can do in the denominator, xk plus xn. So far so good. But okay, we can now say what? For example, we can take this sum yk and substitute for this one. So the sum of y's is equal to, we take an minus 1 times the sum of x's. Good, and let's try to take this one, this expression, and let's plug it in here, right? This sum is the same, the left hand side, so the right hand side must be equal. All right, so we can plug it in. An is equal to what? An minus 1 sum of xk, k is equal to 1 n minus 1. Yeah, that's the thing in the green bubble. What we are missing is to add the last measurement of the output. Yn, and now what? Still divided by the sum of k equal to 1 xk plus xn. And what do we need to do now? Basically, what would be your idea? How we can eliminate the an minus 1 from here? Sorry, there should be n minus 1. Like, we can almost divide this, right? Almost. But we only have this term, which is messing up this plan.
Into sum, like into two sums, there are some together.
Divide, well, we can divide anything into two sums, yeah, sure. But we want this form, yeah. We basically want to divide here by this number, or it's better if we divide this by this number, and we will get just the parameter a. Yn is a times x. Yes, but an times xn. So that doesn't help. That was a good thought. Well, fake it till you make it, right? So let's just yeah. This is. Sorry, n minus 1. Yeah, if we just add this one, then we already in the numerator have an minus 1 times this sum plus an minus 1 plus this times xn. So we can eliminate this. Okay, so if we edit this thing, we need to also, to make it equal, we need to also subtract it, right? Okay, so now we can be already good to go. So we can now definitely, let's try to we can now get rid of this guy, get rid of this guy with the denominator, and we just separate our a and minus 1. Good. What we will be left with? What we will be left with is so maybe let's just write it in the special, slightly special form. We will have let's just keep the numerator denominator separated, and we can write it back as a sum of x's from k1 until n, and what is left is our measurement at time n, and basically minus a and minus 1 xn. Good. Looks good. Looks good. There is what is this one? This one here is the measurement that we have just measured, and we are correcting our parameter a. So okay, something similar that we have here. We should have plugged in the minus to see it better. And what is the other term? Well, this would be just our prediction, but what kind of prediction is that? It's a prediction of the old unupdated model. Yeah, we already know at the time point n we have this value of x, this value of independent variables, but we haven't done this update yet. We are just predicting this value. So this would be our predicted at time n, and sometimes to completely mess up the indices and everything, people would write it in this way. There will be like this pipe and n minus 1, which would mean prediction of the output at time n based on the information I know until the time n minus 1. So I haven't taken this measurement yet, but if I take it, well, I will have a new prediction. So updated value of the parameter times xn. Yeah. So this will be then prediction of n with the information until the point, with all the information until the time point n. Okay, let's write it down. Prediction of y at time point n based on information until the time point n. Okay, and this is basically how our recursive estimation is now working. Like before, what have we studied? Basically, we have our prediction error, and we have some gain. This is how much we are going to trust our measurement in updating our value of the parameter. But this time it's not like it doesn't seem to be our choice. What would happen along the time? So let's say we are just starting with using of our model. We are just starting this recursive estimation. We just measured first x for simplicity. Let's just say it's 1. So we just have here 1 as our gain, multiplying this prediction error. Okay, now if we now get 100 new measurements, so 100 time points passed, let's say that our value of x didn't change at all, so it's 1 all the time. We already have 1 over 100. So our gain is already much smaller. We are already saying, well, what happened? The parameter an-1, it already had the information of the n time points but 1. So it's if n is large, then it's a lot of information. We don't want this information to be lost, to get lost just by one measurement where there might be possible even some noise in this output. Of course, you might then ask how to cope with this kind of situation. Let's say you have 10 years of data, and 10 years of data are predicting some sort of a correlation between the independent and dependent variable, and well, you just have maybe 5 measurements that are kind of contradicting this previously observed trend. You can very easily limit this part. You can basically say, okay, I'm not going to look at all the possible past data. I just take maybe last month, last half a year. It depends. Now it depends on the tuning, how much you know about your process, how much it can change. Okay, so this is like shortened time window. Shortened time window for more recent updates. Okay, so this was the part with how we can update slopes, or let's say a slope, because well, we kind of assume that a is a scalar. So the question is how this works in the general situation. So in general, this used to be our prediction model. Let's maybe also write it in this way, like at end point in time, this would look, oops, something like this. If we want to update our parameters, this will be the world we are living in. So let's just let's just write this down. The derivation is nice, but it takes some time. So if we now use the same line of thoughts, like how we proceeded with in our simpler case, well, we should recover some similar sort of a update formula. So our previous, and now this is the vector, right? That's why I started to write these funny symbols here, the scalar multiplication. So our new vector of parameters will be updated from the old vector of parameters. Our gain, now this is no, let's write V. This will be the now let's use something which we quite know about. V times xn times what? Let me rewrite it, because I wanted to first write it with a shorthand notation, but I'll just simplify it. X transpose X inverse. We have xn, and we have our prediction error. So X transpose n times p. Pn minus 1. This is how it would look in a completely general case. We still have the same ingredients. Yeah, there is the prediction error. Our, sometimes it's called a priori information, a priori knowledge about the parameter. And of course some gain. If you observe this gain closely, well, what we have here the number of the historical values of x. Yeah, this is really those that covariance matrix, and its inverse. So something similar as if it was in the denominator. So if the number of our past historical values of x grows, then also our gain gets smaller. Okay. Good. I think that's basically it. If we had more time, and we never have more time in this course, then well, like we made this look similar to our controller, we are one step away from turning this into a sort of a estimator of the states. Yeah, because also things like, so let's say I have x at time k is equal to oops. How should I write it now? X k minus 1 plus bu k minus 1 plus, what do you use at the theory of automatic controls? Maybe some gain, and you take y k minus c times xk, yeah, something like this. This is nothing else. If we choose our gain y's, for example, there is the Kalman gain, then this will become Kalman filter, where, well, it's not estimating the parameter, it is just directly estimating the states of a dynamic system, but still the idea remains the same. Well, I have some previous prediction, yeah, from the time point k minus 1. I predict what the xk would be, but, well, I measure something else about the state xk, so I use the update. There is again this gain matrix, yeah. So this is all in all the same stuff. Good. Any questions? Does not seem to be the case.